we were covering last time. This chart. And this chart I mentioned covers a variety of some algebraic, some let's call it, well, trigonometric, right? These are trigonometric here. Right, those are, so there's really not any calculus on the slide. What there is on the slide are techniques that simplify a problem in order for you to be able to employ calculus. Right? So I went through a few examples, just completing the square. My hot spots here, to use a term we used before, would be completing the square. Do you know how to do that? Hot spot's number one. Then here, you need to know the antiderivative of that is arcsine. So that's 6, 5, 7 material. Then down here, technique we have where we, when you have the same power, same degree in numerator and denominator, you do long division, and the long division, that is hot spot number one here. And hot spot number two would be, once you get it broken up like that, do you recognize this as arctan? So we've been working on getting the derivatives ice cold, but we also have some antiderivatives to get ice cold that are going to be needed. And so all those inverse trigonometric forms, and I mentioned this last time. I'm going to underscore this. Down here, this table here, and particularly this last half, really, right? All those trigonometric ones, right? All those trigonometric ones, and then these right here with the inverse trig functions, numbers 16, 17, 18. Those are what we were using. We used arcsine last time. We used arctan last time. Right? There's no getting around those. Those are going to be used heavily in this chapter. Heavily in this chapter. All right, so we wound up, oh, here's another one where we took the numerator and we turned it into the derivative of the denominator. You just had a 2 up there, 2x up there. We added a 2, subtracted a 2. That created this 2x plus 2, which happened to be the derivative of the denominator. After that, however, after that, you wound up with this left over. You need to know how to find that antiderivative, right? And that is I did the u du substitution there. Last one is using trig identities. There are a number of trig identities that, and there's going to be a slide coming up here. You'll see trig identities that you're going to especially be using a lot. And so this is you see this and you don't know how you could use it with calculus, all right? Well, let's do the integral of 1 plus sine x dx. What is the antiderivative of that? Well, this doesn't fit any of the forms we have. The bottom, you don't have the derivative of the top and the bottom. If you had a cosine here, if you had cosine right here, you'd be golden, because the top would be the derivative of the bottom. So that would integrate to natural log of the absolute value of 1 plus sine x plus c. But you don't have that cosine on the top. And so this is a algebra, but also involves trig technique, where you multiply the top and bottom here by the conjugate. You have this in the bottom, its conjugate has the negative there, right? So you multiply by 1, and you're going to see this in with other trigonometric functions. You're going to see it with, like, cosecant and so forth. And so you're going to multiply by 1, but you're going to dress 1 up like this. That green stuff equals 1. So never underestimate the power of multiplying by 1 in a helpful format. What is that going to do? Well, multiply across the top. You're going to have integral 1 minus sine x. The bottom, you should treat like this. 1 plus sine x, 1 minus sine x. So algebra technique, a plus b times a minus b is a squared minus b squared. So this is going to be 1 squared minus sine squared. No, you cannot do this. Oh, every time you do that, a kitten dies. Oh, no. You can't cancel terms. You can only cancel factors. You can't cancel terms like that. Well, that denominator, this equals cosine squared. Sine squared x plus cosine squared x equals 1. So 1 minus sine squared is cosine squared. Haven't done any calculus yet. All this has been algebra using trigonometric functions. Now, in this last step, we employed a trig identity. That 1 minus sine squared was cosine squared. Well, what do you do with this? You're going to break it up. 1 over cosine squared minus sine x over cosine squared x. What's 1 over cosine squared equal? 1 over cosine squared is okay. What's that?
1.
1, 2, 3, 4, 5, 6. We have 4. It's not 1. What's 1 over cosine? You need to go.
1 over sine.
I missed this before. You can go here. Right here. 1 over cosine is secant. Secant right there. Okay. You need to know those. There I'm not kidding. There I'm not kidding. So that is secant x. So 1 over cosine squared is secant squared x. So this is secant squared x. Now, we're going to do a little trick on this next one. Actually, there's a couple ways of doing this. There's a couple ways of doing that. Okay. No big trick. I have cosine to a power. What's the derivative of cosine? Negative sine. So I'm going to rewrite that second one like this. Minus cosine x to the minus 2 power times the sine x in the top. Now, this right here equals cosine of x squared. Now, how about if we made that a plus and put minus sine x over here? This is now a u, and this is du. And like everything else I've said, you need to be able to do that. You need to be able to recognize that. And I'm concerned at the softness I see in that area. So how do we, oh, wait a minute here. We have left off a negative right here. That's the negative 2 power. So when I have u to the minus 2 du. So if I went over here, integral u to the minus 2 du is u to the minus 1 divided by minus 1 plus c. Well, that's the same as 1 over u minus 1 over u plus c. What is u here? Cosine. So that's going to be, oh, we're ready to integrate here. The antiderivative of secant squared. The antiderivative of secant squared. Pop quiz. It's on that chart. Secant squared is the derivative of what? That thing. Cosecant. Reasonable guess. It is
cotangent.
You're getting there. You're getting there. Over here. Up here are your derivatives. The derivative of what is secant squared? Or you can go down here. The integral of secant squared is what? Right here. Tangent, let's see. Because the derivative of tangent is secant squared. All right. So if you don't know those derivatives, you're going to get just incinerated in chapter 8. I don't know how to say that because this is going to come up all the time. And my concern is that you're going to be learning chapter 8 and then back there learning chapter 5 and 3 and all that. See, es demasiado. That's my lousy way of saying too much. Too much. Too much. So this is going to be tangent x. Here, cosine to a power times derivative is going to be minus 1 over u. So that's going to be, no, oh, careful here. All right. So it's going to be a minus 1 over cosine x. But you're not going to leave it that way, right? is 1 over cosine x equals secant. Lots of review in there. Lots of review. And we'll go back to what I've recommended before. You need to go through every electron, every molecule of toner on your paper, or graphite that you're putting down on your paper. Every molecule of that. Go through until you understand it all. There's none of this that can go lacking, and there's no substitute than just spending time on it. It's a time issue. So that's why I went through those. The book does not go through those. The book presents this table and goes on. All right. So I've tried to spend some time to review because of the softness that we have there. All right. Okay. Time for another one. What can we have here? Let's draw some lines. Let's do this, shall we? Three integrals, a tale of three integrals. And it's similar to this example on page 518, which means that you have two sets of these. You got what's on page 518 to go through, and that has has comments and everything. And then it has, here we have this that we're going to work these out. What's the difference between these three integrals? The numerator. There's just a 3 here, a 3x here, 3x squared. All right. Who knows how to integrate any one of those three? Some of those are pretty straightforward to integrate. Others take a little bit of working. All right. So I want you to think. And which one of those three can you integrate? The easiest one, in my humble opinion. Is there an easier one that you think is one of these three is easy? I'll say C. He's going to say C. Which one do you think is easier? My vote would be B. And I'll tell you why. Because what did I say to do when you had these the same power? You divide. That's the same as right here. We have the same power. That's exactly what we have, except with three right in front there. So you're going to have to do long polynomial division on that word. All right. Well, let's go ahead and do it. We ain't afraid of no polynomial division. No. You can't unsee that. You can't unsee that, right? Oh, you're going to have trouble sleeping now at night. Okay, so you're going to do x squared plus 0x plus 4 divided into the numerator, 3x squared plus 0x plus 0. We did this yesterday. What do you have to multiply x squared by to get 3x? A 3. 3 times x squared is 3x squared. If those two aren't the same, you did something wrong. 3 times 0x is 0x. 3 times 4 is 12. Draw your line, and the operation is subtraction. subtraction. 3x squared from 3x squared is a 0. 0x from 0x is a 0. 12 from 0 is a minus 12. So what does that mean? That means that this integral equals integral is going to be a 3 minus 12 divided by x squared plus 4 dx. All right. Uh-oh. Ruh-oh. What's the antiderivative of 3? Both of you should know that. The derivative of what is 3? 3x. So this one's going to be 3x. This one we just did on another slide. Those basic ones at the beginning. Right here. What did that wind up being? We have a 3 minus 12 over that plus 4, right? We have x plus 4 on the bottom, right? The formula we need to use is, it's going to be one of these three. Now look on your paper. You have minus 12 over x squared plus 4. Does that look like this form here? That would go to arcsine. Does that look like this form here? That would go to arctan. Or does that look like this form here that goes to arcsec? Which one of those three does that integrate to? 16, 17, or 18? Well, it doesn't have a square root. 17. Yeah, it doesn't have that square root. So it's 17. So that's going to arc10. Now, in our problem, what do we have? We have x squared plus 4. So u is x, a is 2. Right? U is x and a is 2, and it integrates to that. Right? Now, so this is going to be, put a minus 12 up front. A is 2. U is x. So if you look at that formula, you're going to have 1 over a, which is 1 over 2. Arctan of u over a, x over 2. And that's going to simplify to 3x minus 6 arctan x over 2 plus c. Good news is we have the answer. Bad news is all of that is stuff from Calc 1. We're just putting it together with some algebra up here when we did the long division. Right? Questions on that one? This is the hot spot right here. This is the, you got to be able to recognize what form that is. There's more than one way to do it to arrive at that answer. I picked one way. We might do another one over here, a different one over here. Okay. In fact, let's save the easy one for last. This one looks a lot like that one, right? It's a number over x squared plus 4. Here at minus 12, here it's 3. Right? So if you were sharp, you'd say, hey, A is 2, U is X, just like here. And you'd go right to that formula, and boom, you're done. So you have to recognize that that is an arctan. Now, if you don't have that formula memorized, and sometimes if I'm in a cranky mood, I'll bring out the formula. If I'm in a good mood, I'll do it a longer way. I know that 1 over x squared plus 1 integrates to arctan x. 1 over, down here, 1 integral 1 over x squared plus 1 dx integrates to arctan. That one is simpler to remember. Let's see. That's simpler to remember. But we have a 3 there and we have a 4 there. How do we deal with that? We factor them out. So this is another way of doing that. If you know that formula, jump right to it. But if you can't remember, I like that formula, you know, is it a 1 over 2 there? Oh, you forgot that. Is it U over A? I want my mommy. It's so confusing. It's confused. So what I'll do is I'll factor a 3 out here. That leaves a 1 on the top. I'm going to factor a 4 out of the bottom. Now watch. Gasapa. 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 Right? You're going to have x squared over 4 plus 1 dx. Well, I got the 1. You see what I have down here? Down here, I got the 1 I need, but I got x squared there. Now, watch this. Watch this, folks. If this instead of x squared were u squared, I would need du up top instead of dx. Or maybe I should do it this way. Du here. Same thing. So if I have something besides just x that's squared, I just need its derivative. So back up here. There is something besides x squared. This is actually what? I can bring that 4 out. Then I have integral 1. This is x over 2 squared plus 1 dx. So I'm going to let this be u. If u is x over 2, du is 1/2 dx. So what do? Make some space. I need a 1/2 right there. And if that's a 1/2, this becomes du. But if I put a 1/2 there, I need to put a 2 out here. 2, 1/2 offset each other. So now I have 6 over 2, so that's going to be 3 halves out here. Right? And now this is the integral u squared plus 1 du. What does that equal? That equals arctan u. and I have to replace u. What does u equal? X over 2. All right. So these two would not have been my choice for the easier ones because they involve that arctan stuff. Okay. What would have been my choice for the easy one? Mine would have been B. I'll tell you why. X squared plus 4, what's the derivative of the bottom? The derivative of the bottom would be? Two x. So I need to make that 3 a 2. How do I do that? I factor the 3 outside. Integral. I need to make the top the derivative of the bottom. I put a 2 there. Then, out here, put a half. That integrates straight to 3/2 natural log x squared plus 4, which you don't have to put in absolute values because it's always positive, right? Plus c. And that was easy compared to the other two. Right?
How is that the same to the other one?
What's that? How is that the same? This isn't the same as these.
Isn't?
This isn't. No, because this isn't arctan anything.
I thought they're all like get to the same answer.
Oh, no. These don't get to the same answer. Oh, no. No, they're all different integrals, but they're very similar, right? Because they differ up top. One has just a 3, and one has a 3x, one has 3x squared. But you handle them different ways, even though they're similar. So what this is intended to do is apply the stuff back here. We applied some of this stuff, right? All right. Next. We got 2 of them. Question. Now, you might be tempted to do this. Don't write this down. You might be tempted to say, oh, that is x squared minus 4. I have an x out here. I can make that the derivative and put a 1/2 out here. So I have this to a power, 1/2 power, times its derivative. Here, 2x. The problem is all that's in the denominator, not the numerator. If that were in the numerator, I could do that. Wah, wah, wah. Yeah. How do you handle it? I'll give you a hint. 16, 17, 18. 18, you saw it right away. You see? That problem looks a little bit like this. I have a u, then I have something squared minus. Let's see if that works. Right? Yeah. So if we let u be x, that's a u. That's a u squared minus 2 squared. So u is x, a equals 2. So believe it or not, believe it or not, if you know that formula, if you know your derivatives, or in this case, antiderivatives, this goes directly to what? Oh, yeah, that goes directly to what? This is A. 1 over A is 1 over 2. Arc sec of the absolute value of x. You got to put the absolute value here of x over 2 plus c. You go straight for the jugular if you know that formula. And since we are, what are we? Lazy bottom dwelling scum suckers, that is very appealing to us. We got to know the formula. Now, suppose you don't remember the formula, but you say, it looks like arc sec. So if you don't recognize it as arc sec, you don't have a chance. All you do is you go to the next problem on the test. You have no chance whatsoever unless you recognize it as arc sec. However, an encore solution would be to do what I did a second ago for arctan. Make that be this. Let's factor this 4 all the way out. So it's going to be integral dx x square root 4. Uh-oh. I knew I was pressing it too far. By the way, a lot of this I see, I hope you do, a lot of this I see as helping for the test. Lost. So, just to put things in here quick, this will be 1 over 2 arc sec absolute value of x over 2 plus c. You know the formula? That's a happy meal. If you don't know the formula, you're going to have to recognize that it's arc sec still, or you're toast. So if you don't know the formula, you would do what? It's going to be integral dx x. Let's get rid of that 4. I can bring that 4 out as a 2, so it goes all the way out as a 1/2. Now watch this. Watch this very carefully. Bring that 1/2 out. That's that 4 coming all the way out. Then I'm going to leave some space, integral x square root x over 2 squared minus 1. Up here is dx. Question. Is that in arcsecant form? Answer. Almost. Because notice for arcsecant, I need to have whatever it is I have squared, I need to have that outside the radical. So here I have an x over 2 squared. I need an x over 2 outside the radical. So right here, I need an x over 2. All right? So this is a u. That's u. This is u. What's du? So if u is x over 2, du is 1/2 dx. I need to have du in the top. And so what do I need up top? I divided the bottom by 2. I need to put a half up here. Believe it or not, those 1/2s I added, I inserted, they cancel. I multiply the bottom by a half, I multiply the top by a half. They happen to cancel. I don't have to put anything on the outside to compensate. And here a is 1. Because this is really like a 1 squared. And so in that formula, here a is 1. So that top is du. There's u. I got all the stuff labeled. So that integrates to, I got 1/2 arcsec u d plus c. And actually, it'll be absolute value over 1. I'll do that. I'll do that for emphasis. And technically, out here, I have a 1 over 1. Because, look here, I'm going to add, I'm putting those in just so you recognize the form. Here for arcsec, I have a 1 over a here. A is 1 in what I just did. So I have a 1 over 1, and I have absolute value of u over 1. I know that it equals the same thing without the 1. I want you to remember the form. So these ones, I understand you don't have to, it's the same without them. But what does that equal? U is x over 2, right? So that's going to equal 1/2 arcsec absolute value of x actually over 2 plus c. Which is the same as we got the other way. So if you remember that formula with all the trimmings, you can go straight there. If you like to have a 1 right there, which I kind of do, you can do a little longer. Either way. Bottom dwellers, we like to do this top one. We'd rather remember a formula. But if you don't remember the formula, we still have our screwdriver and pliers to do it the long way. What about that buzzard there? 3 over 2 plus e to the x. Here's a trick you got to remember. You can stare at that one for a long time and not get in it. Because you'd like to have the derivative of the bottom on the top. Right? Don't write this on your paper, but you'd love to have an e to the x up there, right? That because the derivative of the bottom is e to the x. You pull the 3 out, leave the e to the x there, and you have it in the form of a log. Natural log. But you don't have e to the x. So what do? Divide the top and bottom by e to the x. You got to remember this trick. This is one of those, like on the Swiss Army knife, this is one of those itsy bitsy tiny blades that you go like, what does that thing do? Like this little thing here. What does that thing do on a, right there? Right? What does that thing do? All right. This is one of those little tiny blades on your Swiss Army knife. Divide the top and bottom by e to the x. So yeah. Okay. What did that do? Watch. Up top, I have 3 over e to the x. I'm going to bring the 3 out. Let's bring the 3 out. But then I have e to the minus x. Right? Right? That top is, this top right here equals right? So bring the 3 all the way out. This 2 over e to the x is 2 times e to the minus x. And then e to the x divided by e to the x is 1. Does that look any better?
No.
What's the derivative of the bottom? Ooh. If I made this u, du would be what? What's the derivative of that? The derivative of 1 is 0. The derivative of 2 e to the x is going to be 2 times e to the minus x, but a minus would come down. So du is going to be minus 2e to the minus x.
So it's not negative 2x?
Nope. The derivative of the top comes down. So over here, d dx of e to the u, e to some function u of x, is u prime of x, e to the u of x. So the derivative of what's up here comes down, which is a negative sign. The 2 stays there. Okay, I would like to have that up top. So watch, ready? Put a minus 2 there. Now what do I have up top? I got the derivative of the bottom. All this right here, that is exactly du. Oops, this is du. You see how I made it into a du? And I bring out the minus 2? So what does that integrate to? I have a function on the bottom. I have its derivative on top. So that's going to be minus 3 halves natural log of the bottom. Now convince yourself that bottom is positive. E to the minus x is always positive. A positive number to any power is positive. So e is 2.7-ish. So it to any power, even if it's a negative power, doesn't turn it negative. So this is going to be all of this we've done with the same antiderivatives that were covered in chapters 4 and 5 last of Calc 1. What we're doing is we're applying some algebraic techniques to it to get them into a form that we can do something with. Right? By dividing by e to the x here, you can make the top the derivative of the bottom. So remember that trick. That's a trick. That's just a trick. You just got to remember it. All right. This is like wind sprints. Right? This is like wind sprints. What about this guy? That looks a little like You have a square root in the bottom. Complete the square. It's not. That's not in the form of any of the anything on that table. If this were not there, that would be in the form of arc sine. If that x weren't there, but that x is there. Okay. So we are going to complete the square and pray for daylight. I know. Mr. Miller, I didn't want my prayer life this strong so soon. Okay. We're going to dress up what's inside here. It's going to be big, long. Oh, look at that. Square root, big, long. The x at top. Now, I'm going to factor, to complete the square, you need a 1 in front of the x squared term, a positive 1. So, I'm going to write that inside there like this. 1, factor off a negative sign. In fact, you know what I'm going to do? I'm going to leave that like that on the table. And I'm going to copy it down here so you can have that. Because we're going to get, this is going to get messy here. Okay, the stuff's going to get messy. But that is the setup. Convince yourself that when you factor off a negative from the x squared, you get a positive x squared, right? You factor off a negative from the minus 4x, you get a positive 4x. How do I complete the square? Half of that coefficient is 2. Square it becomes 4. So you add a 4 here. Now, with that red, I have changed the value of the bottom. Everything in blue, all I did was rearrange the furniture, right? I put the desks in a row and the chairs in back and the computer over here. That's all I did.
Why plus 4 again?
You take the 4 here, half of that coefficient, square it. So half of that is 2. Square it, 4, that goes there. And what that does, that makes those parentheses a perfect square. So these parentheses are now x plus 2 squared. That's why it's called completing the square. But by putting that 4 there, I change the value under that square root. So I have to compensate. Question. What do I have to put here? What do I have to put here to compensate for that plus 4 that I put there? What do I have to put in the blank? Fill in the blank. Pop quiz. Fill in the blank. Well, let's try out 2. So if I put 2 there, that means I added 4 inside here. So I increased inside the parentheses by 4. But I'm subtracting it. So I'm subtracting 4 and then adding 2. That doesn't cover it. I subtracted 4. I need to add 4. So this is going to be a plus 4. And the reason why, this 4 here that's inside the parentheses, it gets hit by this minus sign. So I really, when I put that 4 inside the parentheses, I decrease the value by 4. So I have to increase the value somewhere else.
So if it's just like 6, we have to put like a 6.
Yeah.
Again.
Yeah. But this is always going to be something squared. And it could be a fraction, it could be 6, depending on what that is. So you take half of that coefficient, 2. Square it, 4. I'm subtracting that 4, so I add 4. Now we did that yesterday. Here, that coefficient was a -2. Took half of that is -1. Squared it, I get +1. That's where that 1 comes from. But I'm subtracting it. So really, when I put a 1 inside the parentheses, since it's being subtracted, I am decreasing the value by 1. And so I have to add a 1 to compensate. And so this right here is a definite hotspot. All right, here's hotspot number 1 there. There's hotspot number 2. It's an algebra technique. Right. So what does that give us? 4 plus 1 is 5. So we do it this way. Integral dx square root. Got to sharpen my finger. Right? 5 minus x plus 2 squared. Question. What form is that in? 16, 17, or 18?
18. I think it was 18.
Which one is that? Which trig function is that?
RC.
Yeah, it's arc sine. So we don't have anything out here. If we had something there, right, we could have maybe sec, but we don't have anything there. So this is arc sine, where this is u. What is a? A is the square root of 5, because this is a squared here, right? So a is the square root of 5. So if you know that formula, that integrates to arc sine. Arc sine of what? U over a. X plus 2 divided by square root of 5. Do I need a 1 over a on the outside here? Do I need a 1 over a on the outside? Yes, I do. Hang on. No, wait a minute. There you go. Let's see. Yeah. Hopefully we squeeze this last one. We're gonna try.
Sir, I think I'm gonna take the test on Friday because we play Sunday and Monday.
Oh, okay. Good. Yours gonna be over there. Look at the notes, study the notes. In fact, why don't we talk about the test instead of use project? Yeah, it's a good idea. If I were you, see here. If I were you, I would be going right down this list. In chapter 7, I always put a list of stuff that will be on the test. Stuff that will be on the test.
Page 68.
Yeah.
It was before the centuries.
Yeah, I'm just trying to think what I did. There we go. Know how to distinguish between disk method and shell method. Know those formulas. Those formulas will not be on the test. There's only a couple of formulas there. And there's a couple of formulas for arc length and surface area. If you've done enough problems, by now you've done several problems in arc length, several in surface area, and tons in disk method and shell method. I'm not going to lie to you. If you haven't done very many of these, you have got a very busy 48 hours ahead of you. You've got a very, very busy 48 hours. I would call it an emergency, right? Because, you know, especially with the extra time we had, being snowed in or frozen in or whatever. Disk method, and you use that for, but disk method and shell method are both for rotated surfaces, rotated volumes. If you have a function of x revolved around the x-axis, disk method. Function of y revolved around the y-axis, it's the same axis, disk method. If it's form x, function of x revolved around the y-axis, shell method. Function of y revolved around the x-axis, the opposite axis, shell method. Cross-sectional method, that's actually related to the disk method. And we did a few oddball ones there in class. That you got to know. Arc length. These, the interesting part, and I've told you this before, is that the functions, because you're going to take a square root of 1 plus the derivative of that thing squared. So if you have the arc length of f of x from a to b is the integral. Remember, the arc length is little s is the integral square root 1 plus that derivative squared, right, from a to b. It's this resulting square root that you got to work on integrating. So the integrals can be sticky, okay? Work problems. What can I say about work problems? We have several in class that we did. How many work problems did we do? 5 maybe? They were long, right? But we did several different kinds. It'll be something similar to something you've seen. Not identical, but similar to something you've seen. Fair is fair. I'm not going to go way out in the boondocks, right? All right. Moments and center of mass. That's those formulas. So we got formulas here, here, these two. If you've done enough problems, if you've done the number of problems, you're going to know those formulas. Trust me, you will. So your mission in the next 48 hours is the pencil, el lápiz, right? To paper. ¿Cómo se dice? Papel, papel. Graphite on paper. As many problems as you can. Right? I'll be around tomorrow. Come by and bug me. You're not bugging me. You know what I mean. Come by. Right? Unfortunately, there's that one day I forgot to record. You know what? I think I forgot to record this last Monday too. Yesterday, I mean. We have. Anyway, you got the notes. The notes are up there. Right? So, graphite to paper as much as you can between now and Friday. That's the key. This is the big equalizer. I learned that the hard way. I don't know what you learned. All right. That is it.